Hi, today we're going to talk about bright line spectrum and what happens when electrons go from excited to ground and ground to excited and back and forth. So what I have done here is I've simply drawn just part of an orbital of any generic atom. And let's choose, let's try something that's a little bit more complicated. We're going to try zinc. And zinc has an electron configuration of 2, 8, 18, 2. Now, zinc has 2 valence electrons, even though I drew another orbital out here. The outer orbital is the 4th energy level, so this valence is number 2. Don't worry about this, even though there is a line there. Now, when zinc gets a little bit of energy added to it, like for example, I could put some electricity in there. If I added some electricity into like a zinc wire, for example, that zinc is going to move faster and faster. It's going to get energized. These electrons are going to have more and more energy. Remember, as you move farther away from the nucleus, the energy increases. Okay, so these electrons have a lot of additional energy, and one of them might bump to an outer level. So maybe what happens is one of these electrons from this orbital bumps up to, say, this orbital. Now if I look at this, it's 2 plus 8, which is 10, 27, 28, 29, 30. I confirm with my periodic table that zinc has an atomic number of 30, so the protons have to equal the electrons in a neutral atom. So because it's 2, 8, 17, 2, 1, a total of 30 electrons, I still know that it is zinc. However, because one of these inner orbitals is not filled up according to the periodic table, and we have something that's different according to the electron configuration, I know that this is excited state. What does this matter? When this has energy added, it goes into the excited state. But it can't stay excited for long, so one of these electrons is actually going to bump back into place. And when it goes from excited to ground state, it loses energy, and that energy is given off in the form of light. Again, when an element or an atom, when an atom moves from excited state to ground state, it gives off energy in the form of light. Write that down. That is the answer to every single question dealing with bright line spectrum. Okay, now, what does that matter? So let's say we have an element that goes from excited to ground. It's going to give off different wavelengths of light. And when you track these wavelengths and you look at them on the spectrometer, what happens is you might get something like this. These are the different wavelengths of light for a certain element. And then you might have another sample like this. This is very similar to the gel electrophoresis that you did in the living environment lab. Now if I had a combination of element A and element B, so this is A and B, I'm going to have to see each one of these lines in my final sample. So this is going to be there, then I'm going to have 2 right here, then I'm going to have 2 farther apart, then I'm going to have these 2 right here, then I'm going to have 1, and then these 2, and this 1. So a sample of A plus B must have every wavelength line from A and every line from B. And most importantly, I could use this one to identify what elements are in it if I know all the wavelengths of all the different elements. And we actually do know the wavelengths of every single element. That's why we can identify what is present, what gases are present on the sun, because we look through a spectrophotometer. And what we see is we look through this tube and we can see the different wavelengths, and we know that it's made up mostly of hydrogen and helium. Okay? There's going to be some practice problems over here. Good luck.